Hi, folks. Today we're going to talk about group theory. And so, group theory is the study of algebraic structures known as groups. And we've already discussed what groups are. Groups are a fundamental structure which are frequently found when we deal with binary operations. Understanding the structure becomes valuable for other fields as well. When we're exploring how things combine, rotate, or transfer states, we usually are using groups. What's nice about a group has all of the core structures you need for a single operation. We're going to explore the structure of groups by doing a deep dive into some of the more commonly explored finite groups. We've already seen the integers are a group under addition, as are rational numbers and real numbers. But to understand our structures, we really want to examine smaller structures. And so we're going to look at some sets which are going to have like 5 to 12 different values, much, much smaller. As a refresher, what is a group? And so a group is a set G with a binary operation star, which satisfies four properties for all A, B, and C in G. And so it must satisfy the closure property, which means A star B must be in the group. It must be associative. A star B star C must be A star B star C, and it does not matter which pair you do first. There must be an element called the identity element, such that A star E is equal to A, or E star A is equal to A. Usually this is going to be a 0 or a 1, but not always. And inverses, there must be an element, or for every element A, there must be an element A prime, such that A star A prime is equal to A prime star A is equal to E. Usually, if we're thinking addition, this is going to be a negative value. If we're dealing with multiplication, it's going to be a fraction. A group is considered an abelian group if it additionally satisfies the commutative property. A star B equals B star A. And so with these definitions, let's start looking at some examples. And our first example is going to be modular arithmetic, which is the remainder from division. So modular arithmetic is a system of arithmetic on the integers where numbers wrap around after a certain value. It's often described in terms of the remainder after division. The point at which the system wraps back around is called the modulus, and we say that two numbers are congruent under a given modulus if the remainder after division by that modulus is the same. As an example, the number 17 under a modulus 5 system would be 2, because the remainder of 17 divided by 5 is 2. Often we will write this using a symbol which represents congruence. And so we would say 17 is congruent to 2 mod 5. We might say 2 modulo 5. Let's practice. And so here's a modulo 5 system, and here's a modulo 12 system. And so let's look at the modulo 5 arithmetic first. 4 is congruent to 4 mod 5. 5 is congruent to 0 mod 5. 6 is congruent to 1 mod 5. Note that in the modulus side, it's always dropping down to some number between 0 and 4. 4 plus 5 is congruent to 4 mod 5. 12 plus 19, that's going to be 31. So 31 is 1 mod 5. 19 plus 12 is also 1 mod 5. 2 plus 3 plus 4, 4 mod 5. And it doesn't matter which ones you do first. 2 plus 3 is 0 mod 5. 1 plus 4 is 0 mod 5. You might notice that I'm sneaking in some of those properties in here. These two are demonstrating the associative property. These two are demonstrating the inverse property. We even have our identity property, 0 mod 5. Similar things happen when we're dealing with a modulo 12 system. And so 4 is congruent to 4 mod 12. 3 plus 3 is 6 mod 12. 3 plus 6 is 9 mod 12. 3 plus 9 is 0 mod 12. 3 plus 12 is 3 mod 12. 100. That's congruent to 4 mod 12. -5 would be congruent to 7 modulo 12. And 1 plus 11 or 7 plus 5 are both going to give us 0 mod 12. We can think of this congruence as equivalence. And if you recall, we have the idea of an equivalence relation. Well, to have an equivalence relation, we have to have three properties: reflexivity, symmetry, and transitivity. And this idea of congruence satisfies all three. 4 is congruent to 4 mod 5. 4 is congruent to 4 mod 12. It doesn't matter. Symmetry. If A is congruent to B, then B is congruent to A. Absolutely, we can go back and forth. If A is congruent to B and B is congruent to C, then A is also congruent to C. If we are dividing by M, it does not matter. We are always going to get the same remainder. This gives us equivalence classes. And so if you recall, we have equivalence classes saying when values are equal to one another. And the equivalence classes in a modulo arithmetic gives us a way of basically classifying numbers. And so in the case of a modulo 5 system, we could say that 2, 7, 12, 17, -3, and -8 are all in the same equivalence class because they're all congruent to 2 mod 5. And so we could classify all of them as being equal to 2. In the case of modulo 12, we could say 7, 19, and -5 are all in the same equivalence class. They're all equal to 7. And so here's a theorem. Given a modulo M system, there are M equivalence classes. In the case of modulo 5, there were 5, given by 0, 1, 2, 3, and 4. In the case of a modulo 12 system, there are 12 equivalence classes, given by 0 through 11. When doing addition in a modulo system, it's usually equivalent to doing addition on the equivalence classes. And so when we're talking about doing arithmetic involving modulo or modular arithmetic, usually we will just focus on the numbers 0 through m-1, whatever that might be. And so let's prove that modulo 5 is a group. And so the set would be 0, 1, 2, 3, and 4. And these would represent the equivalence classes, but we don't have to really worry about that because the equivalence classes we're saying 1 is equal to 6 is equal to 11, and so on. And so we'll just focus on these 5 values. And so let's prove that it is a group. First, closure. If we take any values and add them together, we are going to get something between 0 and 4 because we're always going to just divide by 5 if it's anything greater or less than that. Associativity. When we add any 3 values, we will get the same values regardless of order. We could really just think of adding the values together and then applying the mod 5 rule. Identity property. We have an identity. It's 0. If we take 0 and we add it to anything, we're not changing the value. We also have an inverse. And so 0 is its own inverse. The inverse of 1 would be 4. The inverse of 2 would be 3. We also have commutativity. Much like the integers, modular addition is commutative. If we do 1 plus 2, it's the same as 2 plus 1. Since it satisfies all of the properties, it is an abelian group. And that's kind of nice. That means that this is a very well-structured structure. Modulo M is also a group, and we can prove this the exact same way. And so for a given natural number M, a set from 0 through m-1 under modulo M addition is an abelian group. The proof is exactly the same as for the modulo 5 system. And so no matter what M you choose, a mod M system will always have a group structure. This group pops up a lot, and we have a symbol for it. It's Z quotient MZ. It's kind of a funny symbol, but yeah, it works. Before we do more with this group, let's explore one more group. That way we have something we can compare and contrast. And so our other group is going to be a cyclic group. And you may notice some similarities fairly quickly. And so a finite cyclic group, G star, is a group with finite elements that can be generated by a single element. The order n of the group is the number of elements in the group. So a cyclic group of order n is typically denoted Z sub n. It's called cyclic because it'll eventually cycle back onto itself. When we say that it is generated, what we mean is there's an element which, if we repeatedly apply that element over and over and over again, we are going to hit every single element in the group. This element G is called a generator. So note, a given group may have more than one generator. It's very common for groups to have multiple generators, which generate all of the elements. If the order of the group is n, then applying the binary operation to a generator n times will give you your identity element. Let's actually see what this looks like in an example. And so let's consider a cyclic group G under multiplication of order 5 under the operation of multiplication and generator G. So this group will have 5 elements. It'll have the identity element E and the generator G. To get the remaining elements, we would simply apply or multiply G by itself 5 times. And so we would say we have E, we have G, we would have G times G, which is G squared, we would have G cubed, and we'd have G to the 4th. As soon as we multiply by G again, we would get G to the 5th, which we're calling our identity element. Since each element is repeated multiplication, it satisfies the associative and commutative properties. It has the identity element E, it's right there. And the inverses are also there too, because G times G to the 4th would be G to the 5th. G squared times G cubed is also going to give you G to the 5th. And so this is an abelian group. We would denote it Z5. Now, you might notice that Z5 and our Z over 5Z, the modulo 5 group, are very, very similar. And they are extremely similar. Many would say they are the same group, but they're not quite. One was under addition, one was under multiplication. But they have the same properties. They both have 5 elements. They're both abelian groups. And also note that our modular system, that was a cyclic group. If you let 1 be the generator, well, 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 brings you back to 0. And so our Z over 5Z, that was a cyclic group of order 5, just under addition instead of multiplication. Because these things are so similar, we would say that these two groups are isomorphic, meaning they're functionally the same. More formally, there's a two-way correspondence between the two functions, which allows us to go back and forth between them. In this case, addition in the modular group works exactly the same as multiplication in the cyclic group. And we can match up all of the values. And so 0 is the same as E, 1 is the same as G, 2 is the same as G squared, and so on. And so these two groups, which were formed differently, ended up being the exact same group. Here's another one. Rotations of a pentagon. And so consider the pentagon to the right. We can rotate this pentagon clockwise to move the point A to where one of the other values is. And so we could say a rotation of R would be a rotation so that the A value goes to where E is located. If we wanted to rotate it twice, that would be 2R. And so that would be going from A to E and then to D. And so that would be 2R. Going from A to C would be 3R. From A to B would be 4R. And if we're going from A all the way back to its starting position, well, we're not really rotating it. So we could call that a rotation of 0 or 1 or what have you. under the binary are, what's interesting is this is the exact same thing. This is still going to be a abelian group. It's got 5 elements, and it's also a cyclic group of order 5. And so this group, this rotation group, is isomorphic to the other 2 groups of order 5, which we've already talked about. They're all the same. And so we now have this idea of isomorphic groups. And so we've shown that for order 5 groups, the mod 5 group, the rotations of a pentagon group, and the cyclic group are all isomorphic to one another. This will be true for other orders also. And so a cyclic group of order M, the modulo M group, the group of rotations of an M-sided polygon, all 3 of these will always be isomorphic to one another. Since we're going to be dealing with these types of things, instead of writing or stating each one separately, we're going to treat them all as though they're the same group. And we'll just call them the cyclic group of order M. And we'll do them under addition because that's probably the easiest one to deal with. And so basically, we're using the modulo M group to represent all 3. And so let's go back to the cyclic group of order 12 and see if we can play with it a little bit more. It has 12 elements, 0, 1, 2, all the way through 11. We know it's an abelian group. It's also isomorphic to a clock. If we think about it, the 0 would correspond to the 12 on a clock, and then the 1 through 11 would correspond to the 1 through 11 on a clock, and then this would be the rotations on a clock. This is also a cyclic group with a generator of 1. And so 1 plus 1 is 2, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 plus 1 is 4, and so on. We would generate all of the different values. It's not the only generator, though. And so if we were to try starting with 5, 5 plus 5 is 10, plus 5 is 3, plus 5 is 8, plus 5 is 1, plus 5 is 6, plus 5 is 11, plus 5 is 4, plus 5 is 9, plus 5 is 2, plus 5 is 7, plus 5 is 0. Using 5, we were able to generate the entire group. There are others also. So 1, 5, 7, and 11 would all serve as generators for this group. Question becomes, what happens if we started with one of the other values? And that's where we get this idea of a subgroup. And so consider the cyclic group of order 12, but now let's try and use 3 as a generator. If we start with 3, well, 3 plus 3 is 6, plus 3 is 9, plus 3 is 0. In this case, we have only attained 4 values, and we would be unable to get the other 8 values. If we look at this set of values, though, the 0, the 3, the 6, the 9, this set is closed under addition. This set is associative. It's also commutative. The set has an identity element. It has 0 in there. And then 3 and 9 are inverses of each other, and 0 and 6 are their own inverses as well. This group is a subgroup. And so given a set, a subgroup is a group formed by a subset of the elements of the original set. And so if you have a set or a subset of a group, which also satisfies the group requirements, then we call it a subgroup. 0, 3, 6, 9, that's a subgroup of Z12. Note, it's also isomorphic to Z4, the cyclic group of order 4. What's interesting about this, well, is if we think about the clock, we can actually visualize this very easily. This would be counting by 15 minutes on a clock. We would be saying if we're 0 would be the 0 mark or the hour mark. 3 would correspond to where the hand is at when the hand of the clock's on 3. So that would be 15 minutes. The 6 would be 30 minutes. The 9 would be 45 minutes. And then we'd go back to the hour mark. This is just counting by 15s on a clock, which is something we all feel comfortable with, I hope. We can say that it's a quarter past or a quarter till. We can say it's half past. And we have an understanding or an understood meaning for what that represents. That's just a group of order 4. That's just this subgroup. Now, depending on the generator you use for Z12, you can actually get other things. And so if we start with 0, we're just going to get 0. That's not that interesting. If we start with 6, we get 6 and 0, because 6 plus 6 goes right back to 0. If we start with 4, we're going to get 0, 4, and 8. If we start with 3, well, we already did that one. If we start with 2, we get 2, 4, 6, 8, 10, then back to 0. And if we start with 1, we get all of them. Note that all of these groups, or all of these sets, are subgroups. And every subgroup of a cyclic group is in fact cyclic. And so we could say that these are isomorphic to our other cyclic subgroups. And so this first one, it's not that interesting. Note that the first subgroup only consists of the identity element. Any group will have this as a subgroup, and it's called the trivial subgroup. It's a group with one element in it. There's nothing really that interesting there. The first 5 subgroups listed, though, are proper subgroups because they are smaller than the group itself. And we can say that H1 is isomorphic to Z1, again, a very silly, trivial group. H2 would be a cyclic group of order 2. H3 is isomorphic to the cyclic group of order 3. H4 is isomorphic to the cyclic group of order 4. And H5 is isomorphic to the cyclic group of order 6. And so we start to see some interesting structures pop up from this. What if we were to do the same thing with Z5? And so Z5, it only had those 5 elements, 0, 1, 2, 3, and 4. If we try and look at the generators of it, it turns out no matter what value you start with, every single one of them is going to be a generator of the entire set. And so 2 plus 2 is 4, plus 2 is 1, plus 2 is 3, plus 2 is 0. 3 plus 3 is 1, plus 3 is 4, plus 3 is 2, plus 3 is 0. Same with 4, it just goes back to 0. So now we can start to ask questions about the differences between a cyclic group of order 5 and a cyclic group of order 12. What makes it so that one of them has so many different subgroups and the other one doesn't have hardly any? Well, here's their theorems. And so let G be a finite group of order M, and H be a proper subgroup of G of order N. Then M is a divisor of N. What this is saying is if we think about the proper subgroups of Z12, well, the orders of those groups were 1, 2, 3, 4, and 6. They were all divisors of 12. We can go back up and look at them. Here we go. And so this was a group of order 1. This was a group of order 2, group of order 3, a group of order 4, and a group of order 6. They were all divisors of the order of the group itself. And so now in the case of 5, well, 5 is a prime number. And so let G be a finite group of order P, where P is a prime number. Then the order, or the only proper subgroup, will be the trivial subgroup. Essentially, the identity element itself all alone is the only finite, or is the only subgroup. And the group will be isomorphic to the cyclic group of ZP. So no matter what, if you have a finite group of order P, it is guaranteed to be a cyclic group. And that's what we saw with Z5. Z5, it was guaranteed to be the cyclic group. Here's a couple practice problems. The first says, list out all of the proper subgroups of the cyclic group Z15. And so that would have elements 0 through 14 included in it. This is asking, what are the proper subgroups of it? For this other one, it's saying, list out all of the proper subgroups of the cyclic group Z17. If you'd like, pause the video, give it a shot. Let's look at the answers. And so knowing that the order of the proper subgroups has to be a divisor of 15, we only have the options of it being 1, 3, or 5. And so looking at this, the trivial group is the only one which is a subgroup of order 1. To have a subgroup of order 3, well, to get back to 15, we would have to start at 5, go to 10, and then we could get to 15. And so our subgroup of order 3 would be 0, 5, 10. For a subgroup of order 5, well, that would mean after applying it 5 times, we're going to get to 15. So that means we're starting at 3. 3, 6, 9, 12, and then that brings you back to 0. In the case of Z17, 17 is prime. Because 17 is prime, the only proper subgroup is going to be the trivial subgroup. And so understanding these groups and these group structures, we now have a way of understanding other things. And we can start to apply them to things like the motions of a clock, but also cases where we're going to be counting in different ways. When do we count by 5s? When do we count by 3s? What if we want to count by 144s? Well, we can do that. It's called a gross, and we often do that when we're talking about things like eggs. We can also think of the graph of the subgroups, because of course, graphs are everywhere. And so when we think about the collection of subgroups, you might notice that there is a structure to them as well. We call this structure the lattice of subgroups, and it's a directed graph. So if you continue in algebra, you begin to analyze and compare these lattices of different groups to better understand their structures. And so note, as we're going down here, we can see all of the different subgroups. And so from Z12, we had 0, 2, 4, 6, 8, 10. Well, 0, 4, 8 is a subgroup of that, and 0 is a subgroup of that. Well, 0, 6 is also a subgroup of Z12, but it's also a subgroup of 0, 2, 4, 6, 8, 10. 0, 3, 6, 9 is also a subgroup of Z12, and 0, 6 is contained within that. These are just listing out all of the different containments from the whole group down to the trivial group. And that's what the lattice of subgroups is. We're going to do one last group example. This time it's not going to be a cyclic group, and we're going to be able to show that it's not a cyclic group. So the Klein 4 group is a group with 4 elements, I, X, Y, and Z. If you want, here's the table of all of the values, but note that if you do X times itself or Y times itself or Z times itself, you're getting the identity element. If you do X times Y or Y times X, you get Z. If you do Y times Z or Z times Y, you get X. And if you do X times Z or Z times X, you get Y. And then the identity element times anything just gives you that anything. And so this is very much a group. It satisfies closure, it satisfies associativity, and you can just check all of the different combinations if you really want to. It's commutative, and it has an identity. And so the Klein 4 group is an abelian group. What's more interesting is when we start thinking about the subgroups of the Klein 4 group. And so note the Klein 4 group is not a cyclic group. It doesn't have a value which generates everything. And if you try and generate things, well, starting with X, X times X gives you I. If you started with Y, Y times Y gives you I. Z times Z gives you I. And then we also have the whole group itself, which is itself a subgroup. Not a proper subgroup, but a subgroup. So as expected, the order of each subgroup is a divisor of 4, so that's nice to see. But the Klein 4 group is different from a cyclic group of order 4. In this case, the Klein 4 group has 3 subgroups of order 2. And so each of these Ix, Iy, and Iz are isomorphic to z squared. If we were to create a lattice showing the subgroups, we would have Ix, Y, Z, the Klein 4 group at the top. It would connect to Ix, Y, and Iz, and then all three of those would then be connected to the group I. And so this group has a very different structure from the groups we've seen before. But we can then start asking other questions. Is it possible to create a group which has two subgroups of order 2? What if it were only having two subgroups of order 2? Is that possible? Why or why not? And we can start looking and thinking about these different structures. What types of things would be modeled by something like this, where we can basically flip things 3 different ways? Well, what if we flipped things in 2 different ways? What if we wanted to flip things in 4 different ways? Is that possible? What other structures might arise from something like that? Well, that brings us to our final thoughts. So there are many, many types of groups, and there are also rings and fields and other algebraic structures which we can explore. We only focused on a few finite abelian groups, which is a very small piece of the puzzle. But when we think of these structures, it speaks to the nature of numbers, sets, and operations in general. And knowing that the integers are a group, we now have a way to think of the even numbers as a subgroup, and the set of any number divisible by m as a subgroup. What about odd numbers? Would odd numbers form a subgroup? Are odd numbers commutative? If we add 2 odd numbers, what do we get? So we can start to ask questions like that. And this will firm up our understanding of the structure of arithmetic and prepare us for structures in geometry and beyond. Essentially, this idea of a group is where we're first introducing the idea of operations. And all of number theory is based on the idea of these operations. When we were talking about prime numbers, well, prime numbers are dependent on the idea of multiplication. Multiplication requires the idea of a binary operation of multiplication. And so up until now, we focused on the structure of sets for sets themselves. Now we have a way to take values and get something new out of it, this idea of the binary operation. All of the mathematics which is taught in K-12 is really focused on this idea of binary operations and understanding their properties, understanding when something is a group or a ring or a field and how all of that connects things together. That'll help you understand all of the mathematics you've learned up to this point. With that, I'll let you get to work exploring where you find these algebraic structures and groups in the real world. Good luck, folks.